First of all, what is Copenhagen? By Copenhagen, I mean the Copenhagen interpretation of quantum mechanics. And what is that? In Copenhagen, you imagine there's a single outside observer who is not part of the system. Very important, they not be part of the system, has control over the system, and can do experiments. Every time an experiment is done, the state of the system irreversibly, very important, irreversibly collapses the wave function. That's Copenhagen. You all know Copenhagen. You use it. It's a brilliant idea, and it's very, very useful. Okay, but it makes an assumption, unrealistic or unfair assumption. The unfair assumption is that there's some sort of uber observer who himself is not part of the quantum mechanical system. The experiment is not governed by the rules of quantum mechanics, but an extraneous new rule involving collapse. Everett's idea, and the basic thought that Everett had, which is all I really want to take from Everett, is we ought to be able to do better, and we ought to be able to think about systems which have many, many subsystems, any one of which, well, first of all, any one of which could be thought of as an observer. They observe the rest of the system, they observe each other, and all of this should be contained within the rules of a single quantum mechanical. But the main point is that these are sort of two useful ways. Well, one of them is useful, the other may be deeper and more general. Okay, so now we're going right there. We're going straight to Wigner's friend. Okay, everybody know Wigner's friend? Anybody here never heard of Wigner? There was Wigner's friend. Wigner's friend was an imaginary character, and Wigner's friend was a part of a cat experiment, I think, that Wigner cooked up, and he just asked himself something like the question, supposing my friend goes in, well, a cat begins in a cat state, half dead, half alive, but let's go further than that. Let's just say an enormous superposition of many states. Wigner's friend comes in and observes the cat. The result of that in Copenhagen quantum mechanics is to collapse the cat wave function. On the other hand, Wigner is waiting outside the room. He can look at Wigner's friend. He can observe Wigner. He could also observe the cat, but these lines here are not the important ones. It's the lines connecting the observers. Wigner can measure Wigner's friend, and he can confirm or find out what Wigner's friend saw. Okay, but Wigner, if he wants to, he may think of his friend and the cat as forming a single system, and before he comes in, how would he describe that system? Well, we know how we describe it. We would describe it by saying Wigner's friend and the cat are entangled. Then Wigner's friend can come in, and so forth and so on. I introduced Einstein over here. I tell a joke that originally I had him called Schrodinger, but the cat got so scared of Schrodinger that he ran away, and I had to call him Einstein. All right, so let's start with Copenhagen. This is step number one. Wigner's friend observes the cat and collapses the wave function. That's the standard Copenhagen picture. Same step in Everett's language. In Everett, I don't know if this is Everett's language or not. This is a language of entanglement. That the two interact and enter into a entangled state. This is a typical entangled state, summed over the cat's and Wigner's friend states. Or we may also find, for example, if we wait a little bit and allow them to evolve, they'll stay entangled, but the entanglement wave function here may change to some general unitary matrix. So a more general version of the maximally entangled state here would involve a unitary matrix here, and that unitary matrix could involve the evolution of the system. But now let's use the fungibility of entanglement to relate this to a question about black holes. We'll take the cat and squeeze him into a black hole. We'll take Wigner's friend, squeeze him into a black hole, and what will we have? We will have two black holes. By virtue of the fact that they were entangled, they will have some sort of wormhole, presumably by some sort of operations. Originally I had said the cat and Wigner's friend can now jump into the black holes. Well, the cat is the black hole and Wigner's friend is the cat hole, so it's a black hole. So we need somebody else. The cat's friend is Alice. Wigner's friend's friend is Bob. Bob can jump into Wigner's friend. Alice can jump into the cat and meet in the center. Okay? That's the idea of going back and forth between basic quantum mechanical ideas and ideas about wormholes in this case. Another way to describe the entangled state, if you like tensor networks, is to say that the cat and Wigner's friend are connected by a tensor network. The tensor network is just another way of talking about the wormhole. And the one thing that happens is as time goes on, the tensor network gets longer and longer as a function, as a consequence of the natural evolution of black holes. Okay, now, step number 2. Wigner's friend has measured the cat. Now Wigner is going to come into the room and measure his friend. Let's see what happens. We start with the entangled state of the cat and Wigner's friend, and then Wigner comes in, measures, and this is the Copenhagen description, collapses the wave function to one of many of the pieces of the entangled state. And let's say that Wigner's friend does the experiment in the z basis. The z basis, we're thinking a bunch of qubits. In some basis makes the measurement. What does that look like? All right, so let's see if we can guess what that looks like. Here's it. I will go back to the tensor network description, but it's not important. The cat and Wigner's friend are connected by this large tensor network that represents the wormhole. And now somebody comes and measures Wigner's friend, projects Wigner's friend onto a simple state, a state which is just a product state, makes the measurement in the z basis, projects Wigner's friend onto a very definite and simple state, and now the two sides are no longer entangled. They're not entangled. Wigner's friend is in a definite state. The cat is in a definite state. If you're interested at all in complexity, I would tell you if this was a very complex state, then it will be the cat which inherits all the complexity. But that's okay. That's not important right here. Let's call this snipping. This is a new geometric concept. Snipping the Einstein-Rosen bridge. Making the experiment at one end of an Einstein-Rosen bridge, cuts it, snips it, like with a scissor. According to Copenhagen, the measurement is completely irreversible. The complexity on both sides grows, but whatever happens, as long as the two ends cannot come into contact with each other, they remain unentangled, and Alice and Bob can no longer meet behind the horizon. So that's the Copenhagen picture of what happens in step 2. Step 2, according to Everett. The cat, Wigner's friend, and Wigner all become entangled in a tripartite entangled state. Remember, they're all in a pure state. The combination of them are in some pure state. First, Wigner's friend has interacted with the cat, made a wormhole, and now Wigner comes and interacts with the assemblage of both of them, and the whole thing enters into some kind of tripartite entangled state. Tripartite entangled state means what it says, 3 entangled subsystems in some way. And if ERB really is true, if ER equals ERB is really true, this tripartite entangled state ought to correspond to some kind of wormhole or some kind of Einstein-Rosen bridge. And if so, a meeting in the interior should somehow be possible. Well, now we have a little bit of a contradiction. The Copenhagen way of saying things suggested that when you snip, it's no longer possible for the two sides to meet in the center. On the other hand, the Everett way seems to suggest some sort of tripartite entangled state, which would involve some kind of Einstein-Rosen bridge, and you should be able to meet in the center. Now, you could stop right here and you could say, okay, you've demonstrated the contradiction. Einstein.
Could you be more explicit about snipping an Einstein-Rosen bridge?
No. I don't think so. It means you make a measurement at one end. You measure one black hole. You make a complete set of measurements on one black hole. Of course, because they become unentangled. If you have an entangled state and you measure one end, You destroy the entanglement.
Okay, so in your
Right.
view, space-time will change
And the space-time will change.
when you make it.
Right. That's the Copenhagen view of it. The Everett way also says the space-time changes, but in a way that corresponds to three subsystems being entangled. Presumably, if we now take Wigner and collapse him into a black hole, then we would have some sort of tripartite wormhole. And I think that's correct. All right, sounds like there's a contradiction. One version of thinking about it, you can't send any kind of message through the wormhole. The other way of thinking about it, well, you have some sort of tripartite wormhole. It ought to be possible to send something, not something through it, but something from both sides which meets at the center. Is there a contradiction? The answer is no, but we need to know a little bit more about tripartite entanglement. Okay, so here's the initial, let's reduce it down to a qubit problem. The cat, Wigner's friend, Wigner, they're all single qubits. The cat and Wigner's friend, after Wigner's friend measures the cat, they find themselves in an entangled state. Wigner hasn't come into the room yet. Wigner comes into the room, makes a measurement. Here's the way the measurement happens. If he starts in the down state, the zero state. If Wigner finds his friend in the zero state, he stays in the zero state. If Wigner finds his friend in the one state, he flips to the one state. That constitutes a measurement. Right? A measurement where the apparatus and the observer and everything else is just one qubit. And that takes you to a state 0, 0, 0 plus 1, 1, 1. It is an entangled state and it has a name. That's called the GHZ state. G stands for Greenberger, Horn, and Zeilinger. This is a sort of generalization of a belt pair to 3 qubits, and it is entangled, but it's entangled in a rather interesting way. If any party, like for example Wigner, is traced over, the other two, let's suppose we trace over Wigner, this will be the resulting density matrix of the cat and Wigner's friend. This is called a separable density matrix. It has the property that it is just the sum of 2 unentangled density matrices, and this kind of density matrix has no entanglement at all between the cat and Wigner's friend. This destruction of the entanglement is a representation of the Copenhagen collapse of the wave function, and that's kind of the end of the story. Okay, but although no two parties in this GHZ state are entangled with each other, each is entangled with the union of the other two. Each is entangled with the union of the other two, and this allows possibilities that Copenhagen would have no way of expressing, not without enlarging the system and using what you said, right? Which I call Everett. All right, okay. All right, let's just come back to cats which are made out of lots of qubits. Here's a cat which is made out of lots of qubits. Wigner's friend is made out of lots of qubits. After step 1, the cat and Wigner's friend. Incidentally, when I speak of Wigner's friend, I'm speaking about a register that has a memory. When you do a measurement, you have to be able to register the result of the experiment. No experiment is ever done unless it's been registered in quantum mechanics. So when I speak of Wigner's friend, I mean a system which has a memory which is rich enough to encode the result of the measurement of all the qubits of the cat. All right, when that happens, the cat becomes entangled with Wigner's friend, perhaps in the form of a product of bell pairs. Wigner's still over here on the outside. He hasn't done anything yet. But then when Wigner makes his measurement, what happens is the system becomes a product of GHZ states. Let me go back a step. I forgot to tell you what this is. This is a little tensor network that just represents the GHZ state. It has 3 legs, comes together at the center, and it's a tensor which simply says that that it's non-zero if all 3 legs are the same, otherwise it's 0. So this is an attempt to try to draw some pictures representing the GHZ state. After the measurement by Wigner of Wigner's friend, what we just get is a product, a tensor network consisting of a product of these GHZ triplets. Each degree of freedom of the cat has now been measured and is now encoded in one of the qubits of Wigner's register.